Yeah, so permutations. So keep in mind, permutations, order matters. I think Germans maybe invented permutations, but I'm not sure. So in this case, we're selecting objects and we are arranging them either in time and space. We're just going to do space. So basically, I want to know, I've got 7 cards, really big cards here. So I've got 7 cards. And I want to know how many ways I can arrange these cards into 7 locations right here. Okay, so when we're doing permutations, it kind of helps sometimes if we make like 7 little boxes. It helps us think about it. 1, 2, 3, 4, that's 5, right? 6, 7. Okay, so instead of going through all of the arrangements, what I'm going to do is I'm going to say, well, the first one, I have 7 choices to put in the first place here, okay? And these are not independent. So once I make that first choice, that card's used up. In my next place, I have 6 choices. And in my next place, I have 5 and 4 and 3 and 2 and 1 choices. Okay, so if I actually multiply that all out, that's a really big number, isn't it? 620. So, oh, wow, I don't even know how big that is. Of course, that's 5,040, just off the top of my head. There are 5,040 arrangements of 7 cards. Now, we have a compact way of expressing this operation on the number 7, and it's called the factorial, and it's expressed this way. 7! Woo! Go 7! And we call it 7 factorial. And so as long as I've got unique elements, I can arrange them in order in 7 factorial ways. And so, yeah, it's pretty much that simple. That's how you find how many permutations of 7 objects there are, 7 factorial. All right, let's make it slightly more complicated. So unfortunately, we are going to use our 7-card analogy. We're just going to extend it a little bit. So I have 7 unique cards to choose from. And I want to know how many ways can I arrange 4 of these 7 cards. And so now I've only got 4 places that I can put the cards. And so I know that in the first place, I've got 7 choices. Okay, I could pick any one of those cards. In the second place, I've got 6 choices. And in the third place, I've got 5 choices. In the fourth place, I've got 4 choices. And then that's it. I've used them all up. Okay, so 7 factorial is going to fail in this case because 7 factorial is going to tell us too many permutations. So there's actually a way that we can express this. We can just use 7 factorial, and we're not using this part, right? We're not going to use, oh, that's even messier than normal. Okay, 3 times 2 times 1. Okay, so this whole thing would be 7 factorial, but I really want to get rid of this 3 times 2 times 1 part here. And so I can just divide by 3 factorial. And this way I can tell how many arrangements of 4 objects taken from 7 there are. 7 factorial divided by 3 factorial. This notation similarly can be compressed, and you'll often see it written this way. So P stands for permutation. I have 7 objects altogether, and I am going to choose 4 of them. Okay. And in general, we say this is n objects, choose R of them. And it can be written as, n factorial objects divided by n minus R factorial. That looks more like an H. Okay, so n factorial divided by n minus R factorial. And so you'll notice that that is 7 factorial divided by 7 minus 4, or 3 factorial. Okay? Oops. So there's the one way of expressing it. There's the general idea. So that is, are objects selected from N? How many permutations are there? Okay, seems more complicated than it is. All right, last kind of problem. You may have noticed that there are dinosaurs up here. And I have to take these back to the kindergarten class right away. So we need to get this done. So altogether, we have 1, 2, 3, 4, 5. We have 6 dinosaurs altogether. Okay. So my first question is, how many permutations, and so order matters, of 6 dinosaurs are there? Okay, very good. And can anybody out there figure out how many permutations of 6 dinosaurs there are? You don't have to like say a number or anything like that. You can just tell me how to calculate it. So yeah, 6 factorial. And I think that is 720. Okay, so there are 720 ways that I can arrange those dinosaurs. Okay, now, I think I've got some tape somewhere in the room. Tape, Scotch tape, tape, tape. Where did I put it? Okay, maybe I don't have tape. That's all right, because here's my question. I was going to use tape, but it's right here. Okay. So how many permutations are there? Oh, look at what's happened to our education system. There's no Tyrannosaurus Rex. Are there if and so this is a Stegosaurus, and this is a Triceratops. Okay, so how many permutations are there if the Stegosaurus has to be beside the Triceratops?
Oh, God.
And I can just hear the internet right now saying, oh gosh, that is really hard. Oh gosh, how are we going to figure this out? How many permutations are? So this Stegosaurus has to be beside the Triceratops. Come on, toughen up. No, we're not going to do that. Ordinarily, you would say that to like the Stegosaurus beside the Triceratops. So here's what I'm going to do to count this out. I hope whoever I stole this tape from doesn't care. I'm just going to fix this up. I'm going to tape them together. Hopefully they don't like this so that they never ask for this again. Okay, there we are. Now, the Stegosaurus is beside the Triceratops. As you can see, no matter what you do, you can't get them apart. And so now we're ready to solve this problem. How many permutations are there if the Stegosaurus has to be beside the Triceratops? So out there on the internet, Mexican cat dance or duck? Can anybody tell me how many arrangements there are, or how you would calculate that? 6 dinosaurs. 2 of them have to be together, so I'm sensing 5 factorial. Yeah, this is like arranging 5 objects instead of 6, because 2 of them are taped together, except for one thing. Except for one thing. Okay, and you'll notice what the actual problem is here. I have them taped together in a particular order. I have the Triceratops and then the Stegosaurus. And so 5 factorial doesn't quite do it. So I'm going to multiply it by the number of permutations of the stuck together objects. Yeah. So it's 5 factorial times 2 factorial. And saying 2 factorial is just exactly like saying 2. But if there were 3 dinosaurs that had to be together, then it would have been 4 factorial times 3 factorial because I could permute the ones that I'd taped together. Okay, so there we go. This is the special case where objects need to be beside each other. You just you treat it like you've got fewer objects, and then you count the number of permutations where they're taped together. Okay, but, and this is why I actually wanted a Tyrannosaurus Rex, because the real question would be, how many permutations? Oh, what is this as a number? It's like 240. Okay, how many permutations are there? So how many ways can I arrange these, even with these guys taped together? And now, if this was a Tyrannosaurus Rex and a Stegosaurus, they don't want to be together. Are there, if the Stegosaurus can't be beside the Triceratops? Okay, so in other words, it's the opposite problem. Rather than having them stuck together, I want them not beside each other. So this suddenly becomes this really way super harder thing to figure out. How am I ever going to do this? Well, I know how many total arrangements there are. And these total arrangements count arrangements where they're stuck together or arrangements where they're not stuck together. Okay? And so basically, all I really have to do is I have to take 720 and subtract 240. And what I'm going to have left is, oh man, I have to do math here. That's going to be 480. So there are actually 480. And so I am using that indirect method to calculate this. Otherwise, it would be an almost incalculable problem. I'd need to figure out a different way to do it other than treating them like as if they were taped together. Okay, so that's it. That's permutations. It's permutations provided there are no repetitions. Okay, so no similar dinosaurs or cards or things like that. And includes permutations problems that have indirect counting in them. That's it.